Hey everybody, Dr. A here, and in this video we are going to provide a brief discussion on statically indeterminate axially loaded systems. So we're still talking about axial systems, and if you check out some other videos, we explicitly explore axial systems, and these are systems that, or members that are supporting primarily loads acting along their longitudinal axes. And so now we're talking about this idea of being statically indeterminate. Well, what does that mean? So let's write this down. When a system has more unknown reactions than applicable equilibrium equations, it is called statically indeterminate. So basically, whenever you have a system that would have more unknown reaction forces or moments develop than you have equilibrium equations, then applicable equilibrium equations, it is statically indeterminate. And that's true for any kind of system, not just axially loaded systems. But again, we're going to specifically talk about axially loaded systems. So let's look at some examples of this, just some conceptual examples of this. If we have, so we'll say e.g., if we have a bar that is fixed at both ends, like this, subject to some known, loading, call it P. Let's say that's a known load, okay? What happens here? Well, you have two axial reactions that could develop. If this is point A, you would have an axial reaction FA that forms, and if this is point B, you would have another different axial reaction FB that forms here. So the question is, how many applicable equilibrium equations do we have for axial systems? Well, we'll make a note here. For an axially loaded bar, we have one applicable equilibrium equation. Now, you may be thinking to yourself, whoa, wait a second, Dr. A, that doesn't make sense. I can sum forces in the x direction, I can sum forces in the y direction, I can sum moments. Well, all that's true, but for two-dimensional rigid bodies. When you have the specific case of an axially loaded system, then that means that all of your applied loading is along the longitudinal axis. That means that you only have one applicable equilibrium equation, and that is that sum of the forces along the longitudinal axis equals 0, okay? And in this particular illustration, we'll say e.g. the sum of the forces in the x direction equals 0, okay, for this illustration. That's it. I mean, you can try to use some of the forces in the y direction, but since nothing is applied in the y direction, you're going to have nothing when you try to sum forces in the y direction. You could try to sum moments about something, but notice that all of these forces, their lines of action lie along the same longitudinal axis of the member, and so there's no moment or rotation generated in an axially loaded bar by itself. Okay, so that means that you only have one applicable equilibrium equation, in this case sum of the forces in the x direction, but you have two unknown forces that develop, right? So we're going to say two unknown reaction forces develop. And this, in this illustration, would be FA and FB. So what are you stuck with? Well, you're faced with a situation where you have one equation and two unknowns. And so anytime, from algebra, if you have one equation but two unknown variables, you're stuck. You can't solve for a unique solution for both of those unknown variable terms. So what do we need? We're going to say we need another relationship to serve as a second equation. Okay, now this additional equation is going to be based on how the bar will try to displace. Okay, so this additional relationship is based on deformation. Okay? This is called a compatibility equation. Okay? So our second equation that we're going to develop in a situation like this is going to be based on how point A and point B will try to deform relative to one another. And by investigating that and applying our axial deformation equation, that's PL over AE, we will develop an additional relationship called a compatibility equation. Okay. Now, this is one example of how an axial system can be statically indeterminate. We have another case where we can see, we can investigate statically indeterminate systems. So check this out. If you have two materials bonded in a composite fashion, then this type of system will be a statically indeterminate system. Okay, so let's draw this out. Let's say that you have two materials bonded and acting in composite. Let's call this outside material 1, and let's call this inside material 2. Okay, so two materials acting in composite will give a statically indeterminate system. Okay, and so these are two broad cases where we could see statically indeterminate axially loaded systems. We see this first case where you have end restraints, creating an additional unknown, and then the second case where you have two materials acting in composites. Now, what would the unknown be here? Well, you would have a force developed in material 2, and then you would have a separate force developed in material 1. Okay, so here internal forces F1 and F2 represent the two different unknowns due to applied loading. And again, you have two materials bonded such that they're acting in composite. So in summary, statically indeterminate axial systems arise when end restraints give additional unknown reactions, or when multiple materials acting in composite give additional unknowns. In either case, we need a compatibility equation since equilibrium equations will not be enough to solve for all unknowns. Okay, so that's it in a nutshell. That's our background information on statically indeterminate axially loaded systems. In some other videos, we're going to go through some numerical examples illustrating these types of problems. Thanks for watching.